I, Shashi Bhushan Tiwari, welcome you all on this channel. In this short session, we are going to investigate into a theoretical question related to capacitance of a parallel plate capacitor. We all have studied that a parallel plate capacitor, an ideal parallel plate capacitor, has a capacitance given by this formula. Epsilon naught is permittivity of free space, A is area of each of the two plates, and D is separation between them. While deriving this formula for capacitance, we assume that electric field is everywhere uniform between the two plates and it is directed perpendicular to the surface of the plates. With this assumption, we are able to derive this formula of capacitance. Now, at least some of you must be knowing that this is an ideal case and reality is not exactly like that. There is fringing of field lines near the edges and it is not exactly right to consider the electric field to be normal to capacitor plates at points like this. So, this formula obviously is an approximate one. Now, the question is, if we consider fringing of field lines into account, will the value of capacitance be greater than this or less than this? Understand the question well. I am not asking you to calculate the value of capacitance when fringing of field lines is taken into account. No, I am not asking you to calculate the capacitance. I am just asking, will the value of capacitance be greater than this or less than this if fringing of field lines is taken into account? Think about this for a moment and write your answers in comment box, what you think about it. But here I will proceed with my arguments. Actually, consider that the two plates are circular. You can consider rectangular or square shaped plate also. I have considered the two parallel plates to be circular in shape. Because of repulsion of charges, just because of repulsion of charges, we can make a guess that the charge density on the surface of any of these two plates is not going to be uniform. Because charges on this plate will repel one another, so it is commonsensical to assume that charge density will be higher near the edges. Charge density will be higher near the edges as compared to central region. Same is true for this plate also. What I am saying is, charge per unit area over here and charge per unit area over here, if you compare these two, charge per unit area at these locations will be higher because charges are repelling one another and they spread out. So, because of this, charge density per unit area near the circumference region of the plate will be higher. The electric field value that you write between the plates of the capacitor is obviously sigma by epsilon naught, assuming that charge density is uniform. But it is easy to see now that sigma that we have considered while writing the electric field is actually higher than true value of sigma here. What value of sigma you have imagined while doing the calculation? You have taken Q by A as sigma. What I am saying is, charge density is higher over here. So, naturally charge density at these central locations is smaller than this. The true charge density around the center of the plate will be less than this. So, electric field near the center of the plate, very close to it, will be less than this value actually. The actual electric field will be less, let me call this as E naught. So, actual electric field near the surface of the plate is going to be less than E naught. This is just a guess and it is a wise guess. Now, if you move away from the plate, the electric field will become less stronger, even less stronger than this, because fringing of lines is there. field lines are not exactly perpendicular to surface. As you move towards the edges, field lines become curved like this. So, actually the separation between the field lines or the density of field lines will be higher near the center, and as you move away from the center, the density of field lines will decrease. It tends to decrease. So, therefore, as you move away from the center of the plate also, because the field lines are spreading like this, so very near the center of the plate, the density of field lines is a bit higher than density of field lines here, here, here or here. As you move away from the plate, basically one of the two plates, the density of field lines will decrease up to the center, and then again of course it will start increasing, and it will be same here as it is here. So, when I move from this plate to this plate along this central line, why I am choosing this central line? Because it is reasonable to assume that along this central line field will be directed like this because of the symmetry of the situation. So, for calculating the potential difference, you can take any route from this plate to this plate. This is one convenient route that I am taking, the central line, the axial line. Along this line, field is always directed this way, perpendicular to the surface. But the fact is, field is less than this value, very close to the center of this plate, and it is even less here, it is even lesser here, it is lesser here, and then again it increases, and its value will be almost same at this point as it is at this point. So, the fact of the matter is, when I am moving from this plate to this plate along this line, nowhere field is greater than this. It is actually less than this everywhere. So, while calculating the potential difference, you just assume that this E naught into d is the potential difference. What I am saying is, field is less everywhere along this line than this number. Therefore, the potential difference that you have taken is actually higher. Actual potential difference between the two plates will be less than what you have thought it to be. So, the capacitance is nothing but Q upon V. Q is the charge on the capacitor and V is the potential difference. So, actual potential difference is less than what you imagined it to be. So, when V is less, definitely the capacitance should be higher. So, in reality, the capacitance of such a capacitor will be higher than this expression. Let me make another attempt to explain this to you. Actually, the field lines fringes quite a lot near the edges. There is no valid reason to assume that field will be perpendicular to the surface here. Field lines actually become curved near the edges. As you move away from the center, the field lines get curved. So, that is what I was saying. Field line density is higher here, it is lesser here, it is even lesser here, right. So, electric field strength is decreasing from here to center, and then again it is increasing from here to center of the plate. If you just think of a Gaussian surface like this, when you assume that your field is exactly normal to the walls of the plate like this, and if you take a Gaussian surface like this, the entire flux through this Gaussian surface is due to field lines crossing this surface. Okay, fine. Now, in reality, the field lines are somewhat like this, represented in blue color. If you take a Gaussian surface like this, you can easily see that some field lines will definitely pierce through this surface, some field line will definitely pierce through this surface. So, actually, the total flux through this Gaussian surface is no doubt this Q by epsilon naught. But that total flux is not the flux crossing through this surface. Can you see that? Some field lines are also passing through this surface. So, the total flux through this closed surface is Q by epsilon naught, but flux through this surface is less than this, which again gives you an idea that the value of electric field that you obtained in ideal case was a bit higher. Actually, the electric field here will be a bit less than what you have thought it to be. So, electric field being less the potential difference will be less than what you are taking it as right now. So, for the same value of charge, if the potential difference, real potential difference is less than the calculated value, so obviously the capacitance, real capacitance will be higher than the calculated value. So, please do not forget to like the video. If possible, share it with few of your friends. See you in the next video.